Let me introduce you to the audience, and we'll start. Okay. Today, the Professor Valerio Scarani of National University of Singapore will give a talk on the measuring and using quantum uncertainty. He is a full professor at the National University of Singapore, and he's a member of the Center for Quantum Technologies. And he did a postdoctor with Professor Ji Zhang at the University of Geneva, and he got the PhD and diploma from the École Polytechnique Fédérale de Lausanne in Switzerland. And his theoretical research interest is on Bell non-locality, foundations and device independent certification, and also quantum optics and quantum thermodynamics and foundations of statistical physics. And he worked on quantum key distributions also. He published some interesting books. In 2003, he wrote a popular book, Initiation, La Physique Quantique, and 2010 book, 6 Quantum Pieces. And he garnered a lot of fundings from the, through CQT, I think. And also he received a Paul Ehrenfest Award 2017. And also many other awards, and including IPS World Scientific Medal 2010. And so let's welcome, and Professor Valerio Scarani is going to talk on measuring and using quantum uncertainty.
Okay, very good. Thank you for the introduction. I'm very happy to be here. As everybody says, I would be happier to be physically in Korea, but there are things we have to do without these days. And well, so today, yes, I will speak about this topic of quantum uncertainty. Actually, the title was meant to maybe attract a wider audience because the uncertainty relations are well known, but the correct word probably would be quantum randomness. And I will try to explain these notions during this colloquium. Very well, so let's get started with uncertainty relations, the traditional ones, and I will try to comment about what I consider the limitation of these relations that are, of course, correct. So here is the famous Heisenberg uncertainty relation for position and momentum, derived in 1927. And how is this computed? How would you set about checking this relation? Well, so here is the setup. There is a preparation of some state. So these gray objects are, let's say, particles, all prepared in the same state. And then some of them are sent to a measurement of position and are subjected to a measurement of position. And as a result, you would get a string of values of position, x1, x2, x3, and so on, that, again, are compatible with the state that has been prepared. Other particles would be submitted to a measurement of momentum, and you get P1, P2, and P3, and so on. And then you do the statistics with these numbers, and this delta x and delta p that appear at the top are the variances. So the average value of x squared minus the square of the average value of x and of p, of course. And well, okay, so the quantum theory tells us that these variances are lower bounded by h, the product of these variances is lower bounded by h bar over 2, which means that the distributions of x and p cannot be both arbitrarily narrow. If delta x is very small, or let's say even hypothetically, if all the values of x are equal, so delta x is equal to 0, then you would expect delta p to be very large. The question is, of course, why? And what do we do with this fact? And very early on, Heisenberg himself, after deriving mathematically these relations, wrote a popular text where he tried to give an intuition of why these uncertainty relations could make sense. And he came up with this idea of the Heisenberg microscope. I took the image from Wikipedia. So you see here, probably you see my mouse here. There's an electron, and there is a beam of photons here coming on. And the goal is to measure where the electron is. And so these the diffracted photon, the photon interacts with the electron, gets a little bit diffracted, and is collected in this microscope, and the observer finds the beam. And now the argument of Heisenberg went more or less like that. So on the one hand, the precision on the position of the electron, you can take it as an optical obstacle, or an obstacle whose position you have to infer. And by Rayleigh criterion, this position is essentially proportional to the wavelength of the light incoming divided by the aperture of the microscope. And then, on the other hand, because of Compton scattering, the photon has interacted with the electron. So the electron has got a little bit of a kick. And the kick in direction x would be proportional to h over lambda times, again, the aperture here, because if the kick is larger, then the photon would have been diffracted outside the objective. You multiply these two together, and you get this delta x times delta p, approximately. I mean, of course, this is an approximation, so approximately equal to h. You know, up to factors 2 and 2 pi and something like that. This looks pretty much like the uncertainty relation, at least formally, but it is not. Okay, first of all, the main thing that we have to realize here is that this explanation by Heisenberg assumes that both position and momentum are actually well defined, right? And this delta x and delta p are not variances, but are somehow precisions of the measurement. Indeed, maybe I'm a bit unfair in here, because of course I don't want to say that Heisenberg was silly. Heisenberg was a great scientist, and he tried to come up with something, but unfortunately I have to say that probably this, rather than microscope, should be called mistake, because this has pretty much nothing to do, or very little to do, with the uncertainty relation. One of the reasons I can give for that, there are many reasons. One is that the Rayleigh criterion for localization of an object by a beam is already an assumption, is only right for projection on a screen. If you don't take a kind of flat receiving surface, but you take something more elaborate like wavelets, because you maybe have a prior guess of where the electron could be, then this precision can be increased significantly. There have been some works of my colleague Mankei Tsang in this direction. Besides, as I just mentioned, in particular, this delta P is not a variance at all, but a disturbance. Here, there are not many electrons being measured, and the average value of P squared minus average of P squared being measured is really just how likely is that electron to have been diffracted. More importantly, this is maybe an extension of it. You cannot really see it in this microscope, but we know that an experiments have been made that interferences disappear whenever we have which path information. So in other words, if we measure in an interferometer, let's say with 2 paths, right? If you measure position, if you measure in which path the particle is, then the interferences disappear even if there's no modification of momentum. The two canonical experiments for that are the works of Rauch's group around 1975. This was interferometry of neutrons. And what happened is that in one of the beams, the neutron spin would be rotated by a magnetic field. And the neutron being neutral, right, the magnetic field has absolutely no effect on the propagation of the particle itself, besides flipping its spin. And so by introducing this position measurement by whether the spin is up, it's on the upper path, and if the spin is down, it's on the lower path, then the interference indeed disappear, and the momentum of the particle has not been modified in any possible way. And the experiment of Rempe and others was atom interferometry, similar thing. There's an atom taking 2 paths, and on one of the paths, the energy level of the electron is modified. And again, the laser that raises the level of the electron has no effect whatsoever on the motion of the atom, that is essentially the motion of the center of mass of the nucleus, right? That is much heavier. So in other words, the bottom line of all the discussion is that this is not the correct way of thinking about the uncertainty relations. And in fact, more generally, the uncertainty relation should not be interpreted as saying that our measurements will not be ever precise enough to distinguish, to measure positional momentum at the same time with infinite precision. The statement is different. The statement is that really you cannot prepare a state such that both position and momentum will be well defined. On the contrary, and this is going to be important for something I'm going to say later, this uncertainty relation assumes that the measurement devices are actually very good and very well characterized. So actually, I would say that I will repeat it again because it might be a common misconception, that to say that the uncertainty relations are somehow related to imperfect or imprecise measurement apparatus, it's really misleading. Why they should be well characterized? Well, let me give you two trivial examples, and of course, probably all of you will be able to de-trivialize them. For instance, let's suppose that I made a silly mistake and the device that is supposed to measure momentum actually is another device that also measures position, right? Then what comes out and I think is a measurement of momentum, well, will actually be perfectly compatible with the previous device. So you see, if I didn't characterize my measurement device at all, and what I thought is a measurement of momentum actually is measurement of position, well, the things go wrong. Well, you may say, well, this is very stupid. Whoever would do that? Well, I can tell you a story from my PhD that was experimental. Once I was tasked to detect nuclear magnetic resonance from a copper sample, a bit complicated nanostructure involving copper. And I fabricated my coil to detect the NMR signal using copper. And guess what I detected? The NMR signal of the coil and not of the sample, right? So these things happen, and not only to hopefully experimentalists like me. Maybe less trivial, if the values of the measurement, so you have a device measuring position, if the values are badly calibrated, right? Think of one of these old analog, let's say voltmeters, right? Where you had or meters where you had a needle there moving, and for some reason the spring of the needle is too stiff. And so what you think is 5 volts is actually 10 volts, but the needle didn't move very well. You say, okay, this is another trivial mistake. Yes, but again, this shows you that the calibration of the device matters and may invalidate even the uncertainty relations. In the extreme case, for instance, where I forget to switch on the measurement of position, I will get delta x equals 0, because every single measurement of position will be saying 0, 0, 0, 0, 0. And so they're all equal. And I switch on the measurement of momentum, it gives something, and I get delta x, delta p equal to 0 in full violation of the uncertainty relation. You may say, but again, I repeat again, this is silly. We should not make these mistakes. Well, yes, we should never make mistakes, right? The deep reason for what I'm saying is that in general, the uncertainty relations of that type, there are also entropic ones. I will not enter into those details, but the uncertainty relations for the variances look like the one I've written here. And on the left-hand side, you have things that you can compute with a black box, because you can just run the protocol I showed you before. You have 2 boxes, A and B. You send some particles into box A, compute variances, send some particles in box B, compute variances, multiply, and you get a number. That one doesn't need to be any characterization. However, the bound on the other side is not black box. There is no way, if I give you the box to measure A and the box to measure B, there's no way to measure the commutator of A and B. Obviously, it would not help to measure first A and then B, or first B and then A, because in between the state would be modified. So that side is not black box. That side requires accurate theoretical descriptions of A and B. And that's where I was saying, if you think that B is momentum and actually is position, you get the thing completely wrong. So this is important, that the uncertainty relations that do capture some intrinsic uncertainty of quantum theory, but somehow to be verified or to be checked, they require quantum theory itself. They require a very good description of your measurement apparatus using the language of quantum theory. So you need to translate a measurement apparatus into an operator, which may also not be a completely trivial task. So let's summarize what we have for uncertainty relations, and then I will move on. So quantum theory, interesting remark that not everybody makes. Any physical quantity can be sharply determined. Or, so to be more precise, for any physical quantity that you give me, position, momentum, spin, angular momentum, whatever you want, there exist states in which that physical quantity is sharply determined. However, this is not trivial at all, right? If I were to ask you without knowing it, invent a theory in which things are not sharply determined, probably all of us would invent a theory in which every single object cannot be measured precisely. And however, quantum theory doesn't tell this. Quantum theory tells you that every single physical quantity can be measured sharply, possibly, and can be defined sharply. However, when you start to speaking of a few physical quantities, then some of them may not be sharply determined, and actually most of them will not be sharply determined in any given state. There is something here that a guy called Bornstein said about quantum gravity at this point, but I will not go into these. Now, you could be skeptic about what I said and say that maybe, okay, that's quantum theory, but maybe in reality, all physical quantities are sharply determined, and we don't know, or we cannot do better, at least as of today. So we have found for the moment some technical limitation, and therefore we came across a theory that is effective and features uncertainty. And then maybe one day quantum theory will be completed, namely that we will have a better theory in which those predetermined values that have always been there finally will come to the fore. And of course, most of you, especially those who have followed the colloquium of Francesco Buscemi last week or 2 weeks ago, may recognize that that statement is a statement of hidden variables, or more precisely, deterministic hidden variables, according to which, again, we believe that underlying the truth of the matter is that all physical quantities are sharply determined, but we just, for some reason, we don't see it. We are not able to get there yet. And so this topic of randomness and this topic of hidden variables and indeterminism or determinism of quantum theory and so on, of course, is a long history. Let me just give you the timeline for that. In 1926, Max Born proposed that the wave function that has been introduced by Schrödinger 1 year before, sorry, on the same year, should be interpreted probabilistically. Actually, the square of the wave function should be interpreted probabilistically. And this triggered almost immediately a letter by Einstein, where he says what I've written down there: quantum mechanics calls for a great deal of respect, but some inner voice tells me that this is not the right track. The theory offers a lot, but it hardly brings us closer to the old one's secret. For my part, at least, I'm convinced that he does not throw dice. Okay, well, anyway, whatever Einstein thought about it, Bohr and others endorsed this interpretation and became rapidly the orthodox one. We all studied this. 1927, Heisenberg comes up with the uncertainty relations that are actually correct, and then his microscope that is ill-fated somehow. 1932, John von Neumann, among many other things he's doing at the time, he proves a no-go theorem for hidden variables. So he has a mathematical proof that these hidden variables, these pre-established results, cannot be there. Unfortunately, it will be shown later that this theorem is flawed. So therefore, we cannot really take it because hidden variables can behave in a different way than what von Neumann thought. 1935, the famous Einstein-Podolsky-Rosen paper, and at the same time, the Schrödinger-Katz metaphor. So there again, pointing out that when you have composite systems, the first time probably composite systems are brought to the fore, then quantum mechanics predicts strange things. In EPR is this kind of apparent influence at a distance. In the Schrödinger-Kat is this cat being coupled to radioactive decay. And then since we don't know if the particle is decayed or not, the cat is simultaneously dead or alive. Okay, and then essentially for many years, not much happens. I need to mention that in 1952 and 1957, people came up with what I would call deterministic interpretations of quantum mechanics. So keep in mind that, again, the discussion of whether God plays dice or not is in principle open, but virtually nobody cares. And everybody has endorsed the orthodox interpretation is that period also called shut up and calculate, where the new quantum theory predicts so many interesting things that were not known before, that these matters of interpretation are somehow relegated at the coffee table. And but two persons, I mean various people, right? But especially these two, David Bohm and then Hugh Everett, come up with interpretation of quantum theory that could be called deterministic in a way or another. That I may say something of them later. So it's interesting that the debate, but it's interpretations, okay? And they, by the way, the Bohm and Everett interpretation remain interpretation as of today. And there are people who believe in one or the other, but they remain, as far as we know, unfalsifiable beliefs. And then in 1964 came the theorem of John Bell that you heard about in Buscemi's talk, and that I'm going to demonstrate for you now. So I will present now a proof of Bell's theorem that I call the everyman's proof, in the sense that it's kind of amazing that a theorem as deep as this one can be proved with mathematics that probably a secondary school person can appreciate. It really doesn't require any sophisticated mathematics, but it's very subtle reasoning. So the difficulty is rather to, if there is any difficulty, is to follow the reasoning and the assumptions and to play with them, rather than having to deal with complex mathematical objects. So the setting for the Bell theorem, there are two black boxes that are spitting out random numbers. And we also need an input to these boxes. So we need a button that Alice and Bob, our two favorite players, can choose to push. So Alice can choose either the button on the left or the button on the right, and similar Bob can choose either the button on the left or the button on the right. Each time they push up the button, the box spits out a number. Now, what is the hypothesis that we are trying to test? We are trying to test whether there are predetermined outcomes, and also known as deterministic local hidden variable, shared randomness, pre-established agreement, and all kinds of other beautiful names that they can have. And by the way, I have to say here that the assumption of determinism will simplify the proof, but I will remove it soon. So it's not even needed that that this is determined. But if you think in the terms of the physical motivation for this story, yeah, I mean, what we have in mind is that inside these boxes, there are some physical systems whose properties are all perfectly well defined. And by pushing either of the two buttons, we ask for one property or the other, let's say position or momentum, although in this case, we're going to do it with spins. And the hope is that both of them are actually predetermined. And we are going to discover that it's possible that they're actually predetermined. And the truth will be that we discover it's impossible. So what does it mean that we have these predetermined outcomes? It means, well, that inside the box, I will label the output 0 and 1. It's already determined that if Alice pushes either of her buttons in this particular round of the experiment, the output will be 0, whatever happens. And if Bob pushes the left button, the output will be 0. If Bob pushes the right button, the output will be 1. And this, again, is already written there inside the box, inside your physical system. It's just a matter of revealing it. So for convenience, again, this is a purely mathematical convenience. I could continue with zeros and ones, but to make the proof as simple as possible mathematically, I will just move to +1 and -1 instead. And so now we go to my elementary mathematics. And to elementary mathematics, let's call the A0 the predetermined, supposed predetermined result of Alice when she pushes the left button, A1 for when she pushes the right button, and similarly for Bob. Again, remember, A0 and A1 and B0 and B1 can only be either +1 or -1 in this example. Anyway, it doesn't matter what is inside. What matters is that the box, here, this black arrow, the box will spit out +1 and -1. So here could be a measurement of position that is a continuous measurement. But at the end, whatever happens, there must be a process that transforms this measurement of position is either +1 or -1. For instance, you could say if it's on the left side of 0, then you call it -1. If it's on the right side of 0, you call it +1, something. So whatever is happening in there, I don't mind. All that I want is that at the end, there's either +1 or -1 coming out here. Okay, so the idea of Bell actually is slightly different. This is something that is done 5 years later than Bell, but is to write an expression that is a function of these numbers A0, A1, B0, and B1. And the expression that we are going to use is called the CHSH expression, is like that. Is the product between A0 and B0 plus the product of A0 and B1 plus the product of A1, B0 minus the product of A1, B1. Typically, people ask me, why this one? And the answer is, in first approximation, because it works. There is a much more systematic answer, but definitely this is a number that can be computed if all these A0, A1, B0, and B1 exist in the box, right? If you open the box and you read these 4 numbers, clearly you can compute this number. And moreover, interestingly, this number is either +2 or -2. Let's see why. This is the first piece of elementary mathematics. This is, I don't need. If A0, let's say if B0 is equal to B1, then these 2 terms disappear. And this is just +2A0 or -2A0, depending on whether B0 is plus or minus. And +2A0 or -2A0 can only be +2 or -2, according to whether it was a plus or a minus, and A0 is plus or minus. Similarly, so the other case is what? The other case is where B0 is minus B1. If B0 is minus B1, these 2 terms disappear. And then these 2 will be again +2 or -2. So whichever set of 4 numbers, +1 and -1, you put in A0, A1, B0, and B1, this expression will give you either +2 for 8 of the possible sequences or -2 for the other 8, nothing else. Now, here we have a problem. This is probably the most difficult part for a secondary school student of the whole argument. The problem is that in every round, we can both Alice and Bob can only query 1 button. And maybe what happens in the next round will be different values. So in a given round, for instance, if Alice pushes this button, she would only learn A0. If Bob pushed this button, he would only learn B0. And whatever the A1 and B1 in that particular round were, they will never know. Then the next round, they may push another button, but maybe again, the assignments inside the boxes have been changed meanwhile. So how do you do that? Well, you use the fact that the average of a sum is the sum of the averages, which is used routinely when you compute average of marks or whatever you do, right? So average being a linear sum, it doesn't matter if you take the average of this whole thing over many realizations, or if you take the average of these, the average of these, the average of these, and the average of these, and you sum them. So this is what is written here, right? The average of S is the sum of the average of A0, B0 plus the average of A0, B1 plus the average of A1, B0 minus the average of A1, B1. And now comes the famous Bell inequality, which at this stage is a flash of the obvious, which is that the average of S can only be comprised between +2 and -2, because S itself, if it exists, is +2 or -2. So you never get 3. You cannot get 3 on average by averaging realization of this type. And so you see, this is the Bell theorem according to Clausen, Horn, Shimoni, and Holt, is that if these hidden variables, if these pre-established deterministic variables exist, then the average value of these parameter S should be smaller than 2. And this is exactly what is called a Bell inequality. And famously, quantum mechanics violates this. So if you do experiments with photons or with entangled particles, you may find measurements and procedures that I will not go into now. I can describe them later if you want, but sorry, probably many of you know them, that would comply with this description of pushing buttons and getting plus and minus 1. And however, they lead to a value S for this sum that is larger than 2. Now, let me give you the geometric view of what we are doing here, because this can be useful to fix some ideas and also to maybe remove some of the arbitrariness of what I seem to have said. So what I've drawn here is a point. It's not a particularly exciting drawing so far. And it's the point where all the hidden variables, A0, A1, B0, and B1, have taken the value plus 1. I take a space of probabilities. I will tell you later how big it is. And I represent that particular deterministic assignment by a point. Now, of course, in the same space, I may have another deterministic assignment that is another point. And this is the point, as you can see, where A0, A1, and B0 are still plus, but B1 now has become minus. Great. But now comes a very important observation. What about the line between these 2 points in this geometric space that connects these 2 points? So now this line describes what is called convex mixtures of these points. For instance, if I take a point there, what is that? Well, this is a point, it's on the line where A0, A1, and B0 are always plus. So A0, A1, and B0 are always plus. However, now I am closer to the point where B1 was minus than to the point where B1 was plus. And so, for instance, of course, here's a random, right? But I have a probability of B1 being plus is only 0.3. And the probability of B1 being minus is 0.7. So you see, I'm closer to that. And obviously, all these lines can be realized by suitably mixing these and that. So if I take this realization with probability 30% and this realization with probability 70%, well, I create the point that is here. Now that we've understood these, well, now I can add another deterministic point. Here I change also A1 to be minus. Now B1 remains minus and the others remain plus. And of course, on those lines, I can construct the mixtures between these and that, between these and that. And in the middle of this triangle, I can construct the mixtures of the 3 of them. And then I add another point. Now, why do I add another point? Of course, I need another dimension in principle. Usually, I need another dimension. So this is supposed to represent a tetrahedron. And now I cannot add a 5th point because I would need another dimension, and we cannot visualize things in 5 dimension or embedded in 4 dimension. So, but you see the construction, right? You see that each time you add a point, in principle, you add a dimension. It's not exactly like that. And you come up with a structure that is a closed, like a cube, or like in the case of tetrahedron, but the geometry doesn't really matter. It looks like a convex object with flat facets. And such an object is called a polytope. By the way, so now for the case I'm studying, the case of 2 buttons and 2 outputs, there are 16 extremal points like this one, 16 deterministic points. These you can count yourself, right? There's plus, 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 minus, plus, plus, minus, plus, 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 minus, minus, and so on, right? You just, it's 2 to the 4. They are not all linearly independent, so they will define actually a cube in an 8-dimensional space. This, okay, this you have to prove. That it takes a couple of lines of boring mathematics to prove that. So they don't define a 16-dimensional object, but rather a 8-dimensional object. And now here comes the important point that all observation compatible with predetermined results will be inside that polytope. right? Because all that you can do with predetermined result is to, okay, you fix your predetermined result for one round, and maybe for the next round you choose another one, maybe for the next round you choose another one, for the next round you choose another one, then you go back to these, then you choose 2 times this one, and so on. And any point obtained like that will end up, of course, inside this object. And so therefore, these are the philosophical points. So my first animation was supposed to be these. The facet of this object is therefore what defines a Bell inequality. So for instance, here, actually, I think that my labeling was not exactly accurate, but that's okay, doesn't matter. This could be the facet associated to s equal 2 in my previous expression, and everything inside this polytope will have s smaller than 2 or equal if you're on the facet, and everything outside, if there is anything outside, will represent s larger than 2. Now here, I want to make this small philosophical or pseudo-philosophical statement so I get rid of determinism, right? At this point is where I can get rid of determinism. So now, suppose you have a point that is here in the middle somewhere. Now, because it's a convex set, you can decompose it as a convex combination of these points, as I said before. So you can consider these as I take 20% of the time this guy, 30% of the time that guy, 50% of the time that guy. But you're not obliged to. You know, you may even decide, no, there is a physical process, intrinsic physical process, intrinsically random, that generates the point that I want. So you see, the subtlety here is between the mathematics and the reality, let's put it like that, right? The mathematics tells you any point inside the polytope can be decomposed as a convex sum of deterministic points. This does not force you to believe that that point is actually realized that way. Okay? You may decide that it's not realized that way. The mathematical statement holds, right? But it's like you can have similar things with density matrices, right? The fact that a density matrix can be realized by mixing some states doesn't mean that it has been realized mixing those states. So we, ultimately, when you see this geometric picture, you don't need to postulate determinism. So I postulated determinism because, as I said before, again, it was a natural way to introduce this topic in a historical context. And also it sounds, I mean, the kind of model you want to confront yourself with. And it simplifies the mathematics. Imagine if I had started with this polytope there, I probably wouldn't know where I'm speaking about. Whereas with determinism, I could do my simple proof. But we don't need to postulate determinism in order to satisfy a Bell inequality. Or let me put it differently for the last statement. Just adding intrinsic randomness does not help violating a Bell inequality. Okay, now comparing with the uncertainty relations, what is nice of Bell inequalities is these are really black box guarantees. Of course, one thing you have to assume is that these boxes do not communicate, in particular, the input of one box is not communicated to the other. But let's assume that indeed you are in a situation where these two guys cannot communicate and you observe S larger than 2. Then these, maybe I say differently, these can be fake only if there is this communication. If there's no communication, but there are imperfections in the boxes on the preparation of the states, preparation of the measurement or anything, S can only decrease. Now compare this, remember, to the case of my, so for instance, if I try to violate a Bell inequality with position and momentum, assuming these things exist, and by mistake, I replace my momentum measurement by another position measurement, well, I will not violate the Bell inequality. Whereas I would even violate the uncertainty relations. I would get a nonsensical result in terms of uncertainty relations. So if my measurements here are badly calibrated, well, I will violate less, or I'll violate even not at all. There's no bad calibration of the devices inside the boxes that will help me violate more the Bell inequality. And this is very important, okay? It's really the main difference, according to me at least, between the uncertainty relations and the violation of Bell inequalities as ways of certifying quantum randomness is that if anything goes wrong, the Bell inequality can only go down. So the fact that you see a violation of Bell inequality cannot be faked. Again, unless you allow communication, well, that's something you need to exclude. And here comes the topic of device independence that I understand that Francesco Buscemi brought up already in his colloquium, is that those who build the boxes, the experimentalists we call them, right, in our field, those who are in the lab, they need to know very well what they are doing. Because again, if their measurements are lousy, if their states are not entangled enough, they will never be able to produce boxes that violate a Bell inequality. So the experimentalists need to be very competent and very skillful. But the verifier, with the theorist, the referee of the paper, the user of the boxes, doesn't even need to know physics. The verifier pushes buttons and gets outcomes. That's it. And okay, he has to be sure that there's no communication. It doesn't matter what is inside. It doesn't matter if inside there are photons, there are position and momentum measurement, if there are Bose-Einstein condensates, if there are 5 atoms in a strange configuration, distinguishable particles, indistinguishable particles, quantum fields, it doesn't matter. For the verifier, what matters is I push this button, I get this outcome, I do my statistics. If the Bell inequality is violated, something non-classical is going on. And in particular, whatever was happening here was not predetermined, and whatever was happening there was not predetermined. This is what we call the device-independent level of certification of randomness, because it's independent of the device. So whenever you find someone saying, oh, this is a Bell inequality for photons, or Bell inequality for qubits, that's nonsense. A nonsense that has been written many times in the literature in the past because it took some time to realize these. So I don't want to say that the poor Klitschko and other famous physicists were nonsensical people, but a posteriori, that language is unjustifiable. A Bell inequality is device independent. There's no Bell inequality for qubits or for qubits or for photons or for spins. Okay, so let's summarize the Bell theorem and move on to randomness. So we said that, okay, if these results are maybe determined, then the Bell inequality is not violated. And so the logical contraposition of these is if a violation of the inequality is observed, then the outcomes of the measurement could not have been predetermined. Okay, fair enough. That's elementary logic. And now comes an interesting turn of the sentence that, again, is kind of obvious, but we need to do it. So the fact that these were not predetermined, we can give it a kind of anthropomorphic, or let's say agent type term, is that nobody could have known those numbers in advance. Okay, why? Because if there is anybody who could have known that number in advance, he or she could have written them in the boxes, and therefore they would have been predetermined. So let me say it again. Suppose that a very smart physicist knows in advance which outcome Alice will give for 0, and which outcome Alice will give for 1, and which Bob will give for 0, and which outcome Bob will give for 1. He knows, this smart physicist knows all these 4 numbers. Then the smart physicist could build a box that violates a Bell inequality, but at the same time, he or she has written these numbers into the box, which means they were predetermined. But that's what cannot happen, because it's device independent, because the violation of Bell inequalities shows, irrespective of what the support is, that there is no predetermined outcomes in there. So therefore, a violation of Bell inequality means that these numbers, later I will qualify this statement, but something inside the boxes is unpredictable for all, for everyone. Nobody could have known about them. Okay, and this is what it means random. Random is unpredictable. So let's move to randomness. And randomness, I will speak mostly of philosophy, although you may know that random number generators are also very useful devices. In fact, my friends from Geneva, ID Quantique, teaming up with Korean Telecom or whatever the name of that company is, and other companies have managed to put random number generators in some, I think, Samsung handphone something. Right?
SKT and Samsung.
KT, okay, yeah, that's
SKT.
for the,
yeah.
So, I mean, this means that the random number generators can also be useful, but usefulness is not something I'm really concerned with, so I would rather stay onto philosophy. Okay, just a quick map of randomness. You know, randomness is a very interesting concept. Is what the Greek philosopher would call an analogous concept, in the sense that it has many meanings that are similar but not exactly equivalent. And I will show you many examples just now, so you realize that randomness is a broad idea, all right? And there are related topics that are also analog. So, unpredictable. What do you consider unpredictable? Of course, our fellow humans are often unpredictable, right? You have collective behavior that are unpredictable, like the stock market, like the polls, the crowds, the American elections, right? In some countries, in Singapore, the elections are a bit more predictable, but and of course, the individual behavior, like criminal behavior, of course, is unfortunately often unpredictable, because otherwise we would catch all the criminals, there would be no crime. Passwords, we like to believe that our passwords are unpredictable, because if someone predicts my password, then he can tap in my phone, right? So unpredictability, as you see, is something bad sometimes, because we cannot predict criminal behavior. Is something good, because we can protect our privacy. And it can involve human decisions. And of course, well, here we have somewhere we could connect with the topic of free will as well, right? And this is a very deep and complicated philosophical and neuroscientist topic, right? Do we have free will, and what does it mean? Does it coincide with randomness? Most probably it does not coincide with randomness, but there is something, again, analogous, right? When you speak of randomness and free will, you feel that we are on similar grounds, although not exactly identical. And then there are plenty of processes that are unpredictable for us, not involving humans. For instance, complex systems like earthquakes are hard to predict. In Japan, they know more than in Korea, probably. I don't think Korean is very, although we have volcanoes there. The weather, the noise in a resistor, and these kind of things. There are systems, as you certainly know, that are chaotic, although they are simple, like double pendulum, right? It's a very simple system, 2 degrees of freedom, but is connected in a way that makes it chaotic. And then, of course, is a pseudo-randomness. All the many devices that you have in your computer, if you go to MATLAB and you do the rand 115, right, it gives you a random number between 1 and 15, or 15 random numbers between 0 and 1, rather. And well, that's a pseudo random number generator, right? There's no physical random number generator, but there's an algorithm that somehow it's hard to predict. And then there are what we call intrinsic randomness. This will be the quantum phenomenon. And I will qualify again this thing later. But you see how unpredictability is a very broad theme, right? Now, very, very important. Whenever you speak of randomness, it's extremely healthy to ask random for whom, okay? Which means the following. Who is the person that should not be able to predict the results? Or if you don't want to make it anthropomorphic, which information do you give to the computer or the agent that is not supposed to predict your results? Based on which information something is random, okay? Because unpredictability requires a predictor, requires someone who tries to predict. Otherwise, it doesn't make sense to speak of predictability, right? So random for whom? Example, if you start speaking Korean now, your message, your meaning will be random for me, okay? I have no idea of Korean. When I visited, Jae-Wan gave me his fantastic method to learn how to pronounce the Korean alphabet, which I tried to learn at the time, I've already forgotten, but I still have the piece of paper, but still, even if I can now read the Korean alphabet, I cannot understand Korean, okay? So it would be random for me. Of course, there's nothing random, right? You guys can understand each other in Korean, but it's random for me. If you use RSA to encrypt your data, your cipher is random for someone who does not have a quantum computer, or more generally, doesn't have infinite computational power. Again, you may say, oh, but what if you have a quantum computer? Then it's not random. That's it. So random for whom? It's an extremely important question, and it will come up at the end of this talk. And for me, this is a summary of what I consider a definition of cryptography, right? The drawing is taken from the famous book Animal Farm. If you don't know it, well, you missed the joke. But somehow the idea is, if something is random for me, is bad because I may suffer from it. If something is random for the others, is good because I can protect my privacy. Okay, that's the idea of cryptography. Now, what about Bell and randomness now? So how can we connect the observation that we made before, that the violation of Bell inequalities implies unpredictability for all, with a better understanding of randomness now? So if a setup violates Bell inequalities, before the experiment, the outcomes are unpredictable for everyone, as we said. Now, after the experiment, this is also quite important. After the experiment, the outcomes are still unpredictable for anyone who has not seen them. Now, this obvious statement must be made, because if you are trying to use these random numbers for secrecy, of course, you still need to make sure that there's no spy in your lab, right? If there is a spy in your lab that is looking at the numbers, obviously, these numbers will no longer be random for the spy. Clearly, these numbers will no longer be random for you, right? Because you have seen them. But the idea is that whoever has not seen the screen of the computer, so if I tell you, you know, I've done a Bell test with one of my friends and I got some results, I can give you the perfect description of the experiment. We created that quantum state, we made those measurements, we did it 10,000 times and so on. You have no clue of what we possibly observed. Even if you have an even better description of the experiment than me. For instance, they bought the detectors from that company. Actually, I know very well how the detectors of that company work. I know better than even than Valerio how that thing works. So I have more information. Still, you would have no clue. But of course, if you have seen the results, yes, it's no longer random. And now the last point I want to make here is that the violation of Bell inequality is a quantitative criterion. We can tell how much randomness can be certified. I think I have not put the equation of how do you quantify randomness. So I will just tell you in words. Randomness is quantified by the probability of guessing. So it sounds trivial, right? Yes, it is, but that's how it is. So the larger the probability of guessing, the smaller the amount of randomness in a string. And of course, if the probability of guessing is, it cannot be 0, right? It can be, let's say, if I have to guess a bit, the probability of guessing is 1/2. If I have a string of n bits, the probability of guessing minimal is 1/2 to the n. So I can just guess at random indeed, and then maybe I hit it, right? So, but if the probability of guessing is 1/2 to the n, I have perfect randomness, like a perfect coin. And here, how I connect the violation of Bell inequalities with the quantification of randomness in a very qualitative way. So remember, we have this, what I call the local polytope. Inside this box is everything, every statistical distribution that can be obtained with predetermined results and shuffling over them. Quantum theory violates Bell inequality. So therefore, the set of quantum statistics is larger than the local polytope. It includes the local polytope. You can always do these things with quantum mechanics, but you can do a bit more. It's represented by this circle. And of course, everything that is outside here, these are the quantum results that violate Bell inequalities, all these sectors out there. And now, again, this is a Bell inequality. For instance, this is my S equal 2, is this boundary, S smaller than 2 below this boundary, S larger than 2 above the boundary. And if I have a point that is above the boundary, there is some randomness. If there is a point that is more above the boundary, further from the boundary, I have more randomness. And now if I have a point that is almost on the boundary of what quantum mechanics can do, then I have a lot of randomness. In fact, you can prove that on that boundary there are always, I mean, there is always a way to get 2 bits of randomness per round, which is the maximum, right? You get 2 bits out of a round of a Bell test, and both bits are essentially random. There's nothing that anybody can know about it. Of course, if you are here, then a spy could know something. You don't have a perfect coin. You need to do a randomness extractor and some other things in order to, like von Neumann or whatever, in order to extract like a smaller sequence that looks like a perfect coin. Okay, we're not going to these technical details. If someone wants to know more, we can discuss later. Okay, these are just mathematical things that, so these sets can be quantified in a very efficient mathematical way. So there are efficient ways to, if you give me a probability distribution that violates a Bell inequality, there are efficient ways to compute, or at least to bound, how much randomness you can achieve having those data. Okay, now let's go for the last part of the talk, is about the polemics that one can have about the strong statement that there is randomness in physical phenomena, right? Because it sounds very unsettling for some people. So for instance, you could say, aha, no, I uphold the many worlds interpretation. According to the many worlds interpretation, nothing random ever happens, because what really happens is that there's not a single world, but every time there is a quantum measurement that happens or something like that, the world splits in as many possibilities as there are. And then all these possibilities are equally real. We just live in one of these branches, right? The other friend there is Bohmian, right? So she says, no, certainly there's no randomness in Bohmian mechanics, because Bohmian mechanics is an interpretation of quantum theory in which it has non-local hidden variables, right? So it bypasses the theorem of Bell by saying that, well, something like superluminal influence or a quantum potential that changes instantaneously across the whole universe. And therefore, everything is determined, and what is not determined is determined by essentially communication or by some faster than light phenomenon. And so non-local hidden variable. So therefore, again, everything, if you tell me what's happening there, everything is determined, and I have nothing to do with your randomness. Okay, this guy is more into applications, and he thinks that, you know, what is the advantage of having a quantum random number generator? Classical chaos is just as good. I cannot predict what the weather will be tomorrow. Why do you bother about doing Bell tests and so on? If you want for applications, I just take the weather or a noise of a resistor or something of that type. And of course, there is my friend there with a big head who is a super determinist and thinks that maybe we are in the matrix, maybe we are just, we human beings, and our world is just a computer simulation run by some aliens that we don't see. And therefore, we believe that there is quantum mechanics and, you know, relativity and science and love and, you know, Trump and Biden and whatever, but all these are fictions. And these are just a script being played for us, this kind of universal conspiracy theories that some people may uphold. So what do we do with all these things with our claim that the violation of Bell inequalities demonstrates intrinsic randomness? Okay, my recipe is this. I told you already. You should have known, but you had forgotten for sure, right? Random for whom? And if you answer this question, you will see that all the questions of polemics I raised before vanish, essentially. Why? First of all, random for whom? Do you want randomness for a being in our universe, yes or no? Okay, maybe your answer is no. I want randomness for absolutely any possible conceivable being. Well, then, clearly, a being that is stretched across the multiverse of many worlds, there can be no randomness. Or if you're Bohmian, and if you have a being that is capable of reading this pilot wave or this quantum potential or whatever, then there's no randomness. Or again, if you want these robots that are controlling the matrix in out there, also there's no randomness. Some people ask me also in some talks, they ask me if there is randomness for God. Okay, I will not speak on his behalf, but probably not, right? But fair enough. Now you may say, no, yes, okay, okay, good. No conspiracies, no alternative interpretation. I want randomness for a being in our universe. Great. Now, what do we do there? Do you want the being to be with limited computational power or with unlimited computational power? If you want the being with unlimited computational power, then according to what we believe nowadays, only quantum systems are random, right? Because then for a classical system, a system that obeys classical physics, we could run a perfect simulation and we would find out that, what is the noise of the resistor. Now, you certainly know that this is really ridiculous, right? To have an unlimited computational power is something that, well, that is very strange. Interestingly enough, by the way, historical parenthesis, I didn't put a slide in this talk, but this was noticed already by Laplace. When Laplace, in 1825 probably, or something at that time, wrote the Théorie analytique de probabilité, where he described his Laplace demon, right? That this being that has a full knowledge of all the position and momenta of all the particles in the universe and so on. Laplace adds, if this being has also unlimited computational power or something to this effect, I forgot the exact citation, anyway, it's in French, then this being will be able to compute the future of the universe and so on, right? So it's important to keep in mind this point. And definitely, nobody that I know and no computer that I know has unlimited computational power. But if you want randomness against such an adversary, randomness for such an adversary, with respect to such an adversary, then yes, you have to only use quantum systems. Now, suppose that we are in our universe and with limited computational power, then I agree with one of the fellows before, that classical processes can also be random, provided we are speaking of classical processes that are happening then and there, not pre-recorded things. So this is important because imagine that I have a random number generator, a real one, whatever it is, quantum or classical, in my office. And now I run it, I get a random string. And now I record this string on a DVD. And I send you the DVD in a black box saying, oh, look, here I have a random number generator. And you run all the statistical tests you want, it will look random because it came, the same sequence was produced by a random number generator. However, of course, I could have kept a copy of that thing. And then I would know exactly which random numbers you are going to use. But provided that you're actually trusting that the process is happening under your eyes, for instance, you take a resistor in your lab, you connect at 0 voltage, you connect a voltmeter, and you record the fluctuations of voltage. Normally, you know what happens in this case, you detect the radio, but that's a different matter. It depends on the length of the cables. If you get radio waves, then it looks like an antenna, and then you better remove that. But forget about these details, right? If you trust that the mechanism is actually a random process developing under your eyes, then I agree. For a being in our universe with limited computational power, also classical systems give randomness. There is an advantage of some quantum processes that quantum physics allows for device-independent certification, that you are not reading a pre-recorded DVD, as I showed you before with the Bell test. And this is, if you want, in practice, the disruptive aspect of the violation of Bell inequalities when it comes to randomness, is that you can be sure in a black box scenario that you are not reading, you're not operating a box that is actually reading from a pre-recorded list. It's quite amazing if you think about it. You can certify that without opening the box. So is there randomness? Okay, that is my first conclusion. Well, the violation of Bell inequality proved there is a generation of numbers that were not pre-existing and is random for everyone in this universe. This statement does not rely on quantum theory. You might have noticed that nowhere have I used quantum theory apart from telling you that sometimes these Bell inequalities are violated, but I've never used Katz-Bras operators and anything of that type. So to prove that above that line, right, everything is above that line, creates intrinsic randomness, I didn't need to use any quantum theory. I need quantum theory to tell you that there is actually something above that line. Now, the deterministic interpretation of quantum physics exist. You can uphold them if you want, but they have to postulate physical realities that we cannot access. So Bohm has this physical influence faster than light, Everett has multiple universes. And so if you want to be deterministic, really deterministic in the sense of prediction, to make deterministic prediction on quantum phenomena, and you are a supporter of one of these interpretations, well, you've better have access to the physical influence faster than light or to the multiple universes. If you're stuck in this universe, yeah, whatever you do, for you, random, the quantum phenomena will be random, even if you deeply believe that they are not. Of course, again, you can go very far, and please, so don't go around and say that physics has falsified full determinism, right? If someone is full determinism, a la matrix, or in whatever version you can have there, or for God, well, yeah. But normally that's not the kind of applications that we are considering, right? If you want to keep some secrecy from God, well, think twice, right? But maybe you want to keep secrecy rather from the terrorists, right? Or from some bad guys. So my conclusion is clear that for us in this universe, there is randomness. Even if we had to have one day infinite memory and infinite computational power, which is highly unlikely, in this universe, there is randomness. And again, this is going to stay. This is not an artifact of the current theories. This is not something that a better theory of the universe will change unless there are some strange wormholes or some crazy modification of space-time that, you know, if you tell me that when each time in the lab we create two entangled photons that are massless objects that are wormhole created between them, that's getting very, very crazy, right? Now, last conclusion, is quantum randomness useful? I said already something. Well, quantum random number generators have been already sold, so in a sense it's useful to make money. In many cases, the decision on whether to use a quantum or a classical random number generator may be a practical one, of cost, of speed, of stability in temperature, of integrability in a circuit, right? So for instance, quantum does not mean complex or messy or big labs, right? Your laser pointer contains quantum randomness in a sense. The Samsung telephones now contain quantum random number generators. And, you know, of course, there is an element of selling there that we have quantum there, so it's more secure, but probably it's also that the cost is not too high, and these devices are reliable, because if these devices were to cost 1 million each, well, probably you cannot sell your Samsung device. And finally, okay, yes, if you were to sell, this is still a bit far, devices that violate Bell inequalities, these could be even certified in a device-independent way. And this is my last slide, a famous cartoon that we always show in talks about randomness, of Dilbert going to visit the accounting department, and this is the random number generator that they have, and is given this sequence. And Dilbert so asking, are you sure that's randomness? That's the problem with randomness. You can never be sure. This is very scientifically literate cartoon, because this is technically correct, because this is a black box device. So how do you know how his brain is working? But somehow with quantum, you can be sure, at least in our universe. Okay, I finished my talk. Now, let's see if I can see something there. There is some, I see there's a question in the chat. The question in the chat that you can ask question in the chat. Okay, good.
Okay, yeah. Okay, now, thank you so much for the very interesting talk. And now you can ask any questions to Professor Valerio Scarani.
Hey, Valerio, let me ask a question. Hello, yes. Do you hear me?
Yes.
I understand that, first of all, I enjoyed your, interesting talk. I understand that there is a quantum indeterminism. I mean, so that means, as you pointed out, there is no pre-existing measurement value before measurement and so on. However, this indeterminism is not necessarily equal to, quantum randomness. That is my problem in understanding, maybe lack of my knowledge, but nonetheless, let me briefly clarify my, assertion. When it comes to randomness, particularly in the classical mechanics, then basically it means the ignorance, our ignorance of our system in given system. So particularly in many body system, because there are huge number of particles in our system. So inherently, it is impossible to perfectly know our system. Therefore, there is ignorance. Therefore, it's a randomness and so on. But in quantum physics, on the other hand, even for single particle system, as you pointed out, is an indeterminism, right? Even for single particles. So I think on this idea, you call it random. However, for example, a simple example, if you have a single spin system, they're up, down, and then you are interested in your given state is say x direction, x direction party x direction eigenstate. And if you measure z direction, there is still random, right? 50 up,
yes.
down. So the key is in this case, even though you observe, randomness, quotation mark, randomness, z direction, the randomness came from your incorrect measurement, observable, so to speak. So therefore, in this case, randomness is not necessarily inherent, but instead incorrect choice of your measurement observable. Moreover, even for entanglement, if you consider two level system, but if you consider a single particle system, say 1 4-level system, there is no entanglement whatsoever. So it's a entanglement, to my understanding, is depending on picture dependent quantity. So if you therefore, even in this case, if you choose appropriate observable, then no matter what entanglement, you can exactly determine without any random, you can exactly determine the measurement value. So my question is why there is an inherent random, even though there is apparently in quantum in randomness or indeterminism.
So I think that the answer is that there is no correct measurement, right? So if your goal is to determine the state with a single shot, then indeed, I mean, for that particular task, right, then indeed there would be a correct measurement, as you say. So if I prepare the spin in the x direction and I want to determine its state in a single shot, then yes, indeed, I have better measure in the x direction, not in the z direction, right? But
yes,
but that's not that doesn't how to say, that doesn't exhaust all the possibilities of physics, right? The goal of physics is not to determine what is the true state in a single shot. So give me a reason why I am not allowed to measure a spin in the x direction with a z measurement. Why not? I mean, who are you or anybody else in the world to prevent me from doing that? And then if you're in a classical description, then you would say that there must be, for this particular physical property, which is the spin pointing in the z direction, there must be a determined value. And quantum mechanics, as you know, it tells you, no, there is not.
Yeah, I mean, again, there is absolutely a quantum indeterminism, but
right, and that I think we agree with that. So
here on randomness,
I mean, randomness. Remember, randomness is a predictor-dependent quantity. Is random for whom, right? So even a class, in that sense, there is no deep difference between a quantum and a classical system if the predictor is one of us, unless you want to do device independent certification. And the way to discuss that is not to discuss it, is go to the lab and try. Go to the lab, take a resistor and try to predict exactly the shape of the noise. Exactly, not the qualitative shape. Of course, the qualitative shape is given by the Johnson-Nyquist noise, the square root of temperature and whatever not. But try to, you go on a corner and you draw a wiggly line and then you compare with what your students have measured. What is the likelihood that you get it right? The same, very little, right? So that's random for you and it's random for me.
Yeah, but again, but even in this example, you are telling us about if you have if you are, it is true for example, for Ellis, but there is another guy whose name is Bob, who is more smarter. Then he can choose appropriate, observable, which then observable means in the smart means then he chose exactly observable, the observable which lead to the eigenstate. His eigenstate correspond to a given state. So if you are smart enough, so that you can choose.
Hey, wait a second. It's not a matter of smartness, right? So there's no smartness involved. First of all, if you don't know what is the state, you don't know that you have chosen the appropriate measurement until you make many measurements and you see that on the same state, under assumption IID, by the way. So you're making an assumption that the source is producing the correct, that same state many times and is always the same. Under that assumption, you will know that you have chosen the right measurement only when you have done that measure many times and you get systematically the same result. On a single shot, you will never know whether you have chosen the right measurement or not. Appropriate, as you call it. By the way, is a notion that I strongly disagree with. I don't think there's a measurement that is more appropriate than any other.
Yeah, I understand. Yeah, I agree with you. But basically, but there is essentially there is a quantum indeterminism. But still, yeah, randomness is your randomness probably sounds like different from.
Well, again, go to the lab and predict. This is called Randy test. Go to the lab, predict something, come back and show me that you predicted correctly. If you manage to convince me that, then it's not random for you.
Okay, some years ago, I listened to a mathematician's talk, and he told us that he was asked to check the randomness of some random numbers generated by the ID quantic random number generators.
Yes.
And so apparently he used some criterion used for the pseudo-random numbers. And his estimation was the random numbers generated by the ID quantic was not so random. So it was
okay.
But it should be actually that if something is generated by these quantum mechanics, it should be real random.
No, but okay, there are a couple of confusions there. First of all, I don't know the work you're speaking about, so I should check it too. But let me clarify a couple of things. First of all, what you're referring to there is what we call the product randomness and not the process randomness. So it's the randomness, the statistical features of the numbers created by these devices.
That's right, yes.
It's not a certification that the process itself that is creating that is random. The two notions are similar, but not equivalent. For instance, as you certainly know, I could toss up a perfect coin, perfectly unbiased coin, and get the sequence 0, 0, 0, 0, 0, 0, 0, which would not look like a random number. But it's a possible outcome of that device, right? So and still I could still believe for some reason that the process is actually random, right? So, okay, fine. But that being said, so what may happen there, no physical random number generator is perfect on the spot. So what IdeaQuantic does is after the physical process, they have what is called a randomness extractor, which is supposed to make the randomness unbiased and secret. And now, I can only surmise that maybe what this mathematician discovered is that the whole process is not as perfectly randomized as claimed. That might be perfectly the case, and that therefore you have a coin with a 60%, 40% bias instead of a 50-50 bias. That's, it's not absurd. And it would not be a falsification of the fact that the process is random in itself. It would just be that you can guess, the probability of guessing is not as low as it should. So in that sense, I would not be surprised that.
Yeah, so that means you are talking about the randomness of a process, and he was talking about the randomness, pseudo-randomness of a product.
Correct.
Yeah, okay.
I mean, correct. Again, from what you say, that's what I infer, right? Now, maybe they did something else. That if I don't know the paper, it's hard. But I would surmise this, yes.
Okay.
Excuse me, Valerio, one more question then, if you don't mind. Then your case, theorem, quantum inherent randomness. Then then, as you briefly pointed out, when it comes to, as far as I know, people are still looking for, another alternative to quantum mechanics, particularly in the spirit that, quantum physics could be simply an emergent theory, such as Bohmian scheme, something like that. If it is the case, then your inherent randomness cannot be any longer inherent quantumness, randomness. Instead, it is, it can be, rescued, right? Eventually, right?
Random for whom?
Right, depending on, so then random, exactly. That is then means if you are smart enough, so to speak, quotation marks, smart enough, so that you can control everything, then there is no existence of random.
Okay, as I said, I fully agree with that. If you are so powerful that you can control the quantum potential of the Bohmians, then there is no randomness.
Yeah. So therefore, this is not inherent, intrinsic random whatsoever, right?
Again,
this is for us, because we are.
I think I put intrinsic in inverted commas, and I think I said enough many times in this talk random for whom, and I would appreciate if people who are asking questions clarify for whom they want their statement to be random, and not asking me to quantify on randomness for God. Okay.
All right, thank you.
Okay, may I ask a question?
Yes, please.
Sure, go ahead.
Okay, I enjoyed your talk. I'd like to clarify myself if I understood correctly your message.
Mm-hmm.
So you are saying that the intrinsic quantum, or rather intrinsic randomness in quantum physics is observed by someone living in a limited set without knowing full knowledge. Therefore, it is still some kind of ignorance. Unlike the usual textbook interpretation of quantum indeterminacy.
No, well, I think that first of all, most of textbooks are crap, right? So that's no discussion about that. It's just people repeating what they've learned from what they've learned from what they've learned from what they've learned from some smart guy. I also mentioned that, so what I said is, if, for instance, you are a Bohmian, and let's say, assuming that the Bohmian metaphysics is correct, then indeed, we are ignorant, by definition of the Bohmian model, we are ignorant about the quantum potential. That's right. That's how that thing goes, right? That there is this quantum potential that is infinitely rigid, however, we are not able to observe it.
Okay.
Yeah, okay. Now, if on the contrary, it's a different interpretation, you are, the truth is the many world interpretation, then we are ignorant of all the other branches of the universe, right? So what I want to say is that, of course, and now finally comes what you call the textbook, or maybe some people call it the Copenhagen interpretation, whatever it is, that there is there's no quantum potential a la Bohm, there is no many worlds, there's only one world, and there is intrinsic randomness here. That would be my interpretation, okay? And there is really randomness, in a sense, objective, if you want to call it like that. Again, maybe not for God, but I just wanted to, so my only point was this, that you can have a deterministic interpretation of quantum mechanics, and people do have this deterministic interpretation of quantum mechanics, and these are not in contradiction with the fact that there is randomness for us in this universe. It's just that, as also the previous person pointed out, indeed, if that is the truth, as when we die, we go to heaven and we see the truth as it was, we discover, oh, wow, there was a quantum potential after all. So there was no randomness. But as long as we are here in this earth, right, struggling to make our ends meeting and so on, it looks like both the Bohmians and the Everettians and everybody else will have randomness. In other words, take a Bohmian, your favorite Bohmian friend, bring him to the lab and ask him to predict the results of a Bell test. I don't think he will succeed, right? He will believe that this is predetermined, but he will not be able to tell you what the results of the measurements are.
Yes.
Just make the test. I mean, that's the thing. Make the test. Bring the people. Let's not speak of philosophy. Bring them to the lab, ask them to predict, and let's see what happens.
Okay.
Yes, but one more case.
Thank
Yeah, you point out, in your talk, you said, you also briefly mentioned about the fact that, the von Neumann's, the no-go theorem was flawed simply because he considered only local hidden variable theory rather than non-local hidden variable theory. Am I right?
No. The mistake of von Neumann was to suppose that hidden variables compose in a linear way with a spin direction, something like that. I mean, I should make a technical statement. You can look for so he would try to have a local hidden variable for a single spin, and then he proved allegedly that he could not do that. But then John Bell found a local hidden variable for a single spin, and it's very famous. It's trivial. Trivial. No. It's reported in the appendix of my book on no locality if you happen to have it, and otherwise it's famous anyway. So no, the mistake of von Neumann was really an assumption that the local hidden variables have to compose like vectors, and they don't. So that's what John Bell noticed, and then I think, in fact, the real story of John Bell is that he first found that von Neumann was wrong, and he found a local hidden variable for one spin, and then he went on to look and find the local hidden variable for two spins, and that's how we found that there was none.
Yeah. I read some kind of paper related to this issue. Yeah. I mean, not only the von Neumann, but also another German lady. I forgot her name, but I think you must know this lady. Yeah.
Oh, I mean, I'm sure there are plenty of people. Yes, there are people who have made, but somehow, unless we missed really something big in the last 50 or plus years, I think that John Bell is the one that is really responsible for setting the problem in the way that we have addressed it today. Heisenberg himself had a no hidden variable theorem. They're quite smart, but based on a kind of philosophical claim. His claim was that if the Heisenberg cut is arbitrarily movable, so if there is no real border between classical and quantum world, where you can arbitrarily move these what is quantum, what is classical, then obviously there cannot be any local hidden variable, because you just move the cut a bit higher, and then there cannot be any definite value behind, right? So that was his argument. You can find.
Yeah, I mean, my remark is that I was originally interested in what made John Bell think about this problem. I mean, Bell's inequality itself, as you demonstrated well, is pretty straightforward. But my interest lies originally, what made him think about that. As you pointed out, the people like the John von Neumann and the other people, they already thought about that, and basically John Bell borrowed his idea from the previous work from other people. So it is not completely original. There is not 100% originality. Instead, he was stimulated by other people's previous work and so.
Yep.
Okay, more or less. So it's already 5:30. So Valerio, your book, 2019 book, Bell Non-Locality, and Oxford graduate textbook. This might have some details discussions on this, right?
Yeah, I mean that is of course this one is technical, right? So this is a book that can only be read by people who are literate like you in quantum theory. But I try to condense what I think is worthwhile transmitting to the youth in that particular book, right?
And do you have some other review or something to read easily?
There was a precursor of that, but you can just find some reviews on the archive, or there's a review paper. A review paper is a different thing, right? So this book is really a textbook where everything is done in great detail, and review paper is more the typical thing, like this guy has done that, the other guy has done this, and try to put a bit of order there. We have a review paper out there, 2016, I think. There are some other resources here and there, but I mean, if someone is interested, they can contact me, no problem. I have an email. You can find my email online and just ask questions.
Okay. Okay. Good. Okay. Thank you so much, and so thank you for all audience and the Valerio, and see you in real situation.
I hope so. Yes. Okay. Thank you very much for listening.
Yeah. Okay.
Bye.
Okay. Bye.